Differentials and approximations. In this chapter, we have been studying what a derivative tells us about a function. Lots and lots of properties about functions. After I get through this. Okay? Okay, one of you is going to have to move. I don't really care. I know, but I'm trying to go through this, and then the recording gets all messed up. Okay, we did in chapter 4. First derivative tests, find max mins, we found inflection points, we found concavity. And then yesterday we just did a little bit of a lesson on how can we use derivatives to give us optimization, maximum profits, maybe minimum losses. If you go into business, you have to do calculus, because that's how they do that. If you're also going into marketing, this may also be another application. So you have to take calculus for those classes, for those occupations, because you're actually going to use that. Well, this is just another application of a derivative. We know that. What is a derivative? Okay, so the slope is equal to f prime of x, and that's equal to the derivative with respect to x of some y value, right? That's what that means. Well, what we're going to do here is we're going to use derivatives, and we're going to break this into little pieces and use that to approximate the changes in a function. So if I look at this, this is dy over dx. It's another way we can write it. And if you think about back when we started with derivatives, we took the slope between 2 points. And we called this x, and we called this point a. And it was the limit. This is the other definition of f of x minus f of a all over x minus a. And we would drag x and a closer and closer to each other. Okay, do you remember that definition? It's the one you're probably going to use in science classes, because I can actually see what? What is f of x minus f of a? Isn't that just the change in the y values? Yeah, change in y. What's x minus a? That's this distance. It's the change in the x values. And if x approaches a or a approaches x, what happens to delta x? It goes to what? 0. It's smaller. Well, guess what? That's equal to dy over dx. So if you think of this in a different way, this is an operator. Say, find the derivative, but I also know that dy is pretty close to the actual change in the value of the y on the function, and dx is actually equal to delta x. So there's my picture. I left a space for you to draw a picture. And then I decided I would also try a little technology. So I'll bring that in a second. It's kind of cool, actually, once you see what you can do. Well, I'm trying. Finding time to do it is hard. Okay, so I will redraw this a little bit. Here is my function, which is growing at a faster and faster rate. And if I'm looking at this point here and this point here, then the distance on the y values is called just the change in y. What is change in y? Call this point x1. Call that point x2. What is change in y? It's f of x2 minus f of x sub 1. There's nothing new here. That's just the change on the function of the y coordinate. We've done a lot with lines. In fact, I did lines in pre-algebra this morning. So it's just the change in the y values. What's interesting, though, is if I use a tangent line, I can find another way to find something that's not quite equal to it, but close to it. Now, what is this little distance here? This is the actual change in y. This is the actual change in x, right? That makes sense? What is the change in x? It's x2 minus x1. That's all change is. So this is the change in x of the curve, and this is the change in y of the curve, this length, that full length here. But if I draw a tangent line now, and we're going to do a little bit of arithmetic here, or algebra, what's true about the change in x of my tangent line? What's true about dx and delta x? Look at the picture. Are they different? No, they're the same. But we'll have to look at this. Let's take this derivative we have here. We have f prime of x is equal to dy over dx. And that's the slope of the tangent line. Think of that dy as the change in y along the tangent line. That's this segment. Is dy equal to delta y? No. Dy does not equal delta y. But what if delta x is really small? I'm out of colors. Oh, I could write black. What if delta x is tiny, tiny, tiny? What's true about dy, which is the change on the tangent line, and delta y, which is the change on the function? They're pretty darn close. They're really close. So I can use calculus to find an approximation to the actual change in the function. Some of you are thinking, well, why would I do that? Well, sometimes calculations can be quite complicated, and the calculus is actually easier. And you're still going to say to me, well, I have a calculator. It's not that complicated. You have to keep in mind that the calculus was invented or discovered, whatever, however you want to look at it, back in the 1700s. You didn't have a calculator until 1973. That was really the first decent calculator with a trig in it. So we use calculus to do a lot of this stuff. It's on the exam. We always like to do approximations. It does make some things easier, even though you're right, I could do it with a calculator. So we'll do some of that. Okay, so if I think of my slope of my tangent line as dy over dx, this takes on a new meaning. This is the change in y on the tangent line. Now what I'm going to do is, now I'm thinking of this as increments on the tangent line. That's the y, that's the x. That means those are just numbers. Can I solve this equation for y? By the way, that's the first box here. dy dx equals f prime of x. Could I solve for just dy if I think of it just as a number? What would I do? Multiply by what? dx, right? So dy, because the dx is cancel here, is equal to f prime of x times dx. That is called differential form. So it's now thinking of dy and dx as separate little numbers, actual changes in values. This is the derivative form. And you'll get it. It'll just kind of happen. And we have to have this differential form second semester to do what we're going to do. Lots of geometry second semester. So I'll get rid of this little box. And there it is. So we'll do some problems, and that's what this lesson's about. Tomorrow we will write the equation of the tangent line, and you'll see how these connect. So notice the assignment, when I get to the last page, I'll show you what the assignment is, because we're not going to start at the beginning of the assignment. We're doing it reverse of what the book's doing. Okay, on the bottom of your first page, if we want to estimate the change in some function, that's the actual change in the function. And I'm going to change the x's a little bit. We can approximate delta y by dy. And it's usually easy to do the calculus. Delta y represents the change in y on the curve. That's where we have the problems, keep them straight. Dy represents the change in y on the tangent line. So what I'm going to do is something a little different than I did in second hour. I'm going to do the same thing. I'm going to write that in differential form. But let me show you an example what delta y and what dy is. A simple example like this. So the easiest way for me to write that in differential form, honestly, is to say y equals x squared and take the derivative of both sides. So what's dy dx is equal to what? 2x. Now, solve for dy. What's dy equal to? Multiply by dx? Yeah. That's what they mean by differential form. So when you get to homework problems like that, they're pretty easy. The homework problems are meant to guide you, to help you know what those words mean. Well, let's look at the picture. Let's see what that is. And we know this is a parabola, right? And let's take x equal to 1 right here. And I'm not going to draw it to scale. And then let's let delta x equal 1. So my lesson's a little different. Pretty much not. So where am I over here then? If delta x equals 1, I'm at 2. Whoopsie, that's 1. And I can find the actual change in the y value because this is 1, f of 1, and this is 2, f of 2, right? So this ordered pair is 1, what's 1 squared? 1. And then this is 2, and this is 4. So if I'm asking for delta y, I'm just asking for that, the difference between 4 and 1. That's all I'm asking for. So delta y is equal to 4 minus 1, which is equal to 3. Now, the parabola is changing pretty fast. Changing at a faster and faster rate. What's dy? Well, we have it from here. dy is equal to 2x dx. Now, x is where you drew the tangent line. I'm going to draw the tangent line because I haven't done that yet. So now we're going to find the change on the tangent line. Okay, so there's delta x and dx. They're the same. This is dy. So I can find this length. Well, what is dy? dy is equal to 2 times my x. Where did I draw my tangent line? At x equals what? 1. And then dx, what's delta x? From 1 to 2 is what? 1. So my approximation is 2. Is this an overestimate or an underestimate? Here's the real value, the real y value. Here's the one on the tangent line. Will this number be smaller than the actual change in y or bigger? Smaller. Okay? So that's smaller than the actual change in y. And that was 2. And delta y ended up being what? 3. Not all that close. But you know what? I'm not very close to 1. And that's growing very quickly. Really, I'd rather have something smaller. So actually, I brought up my calculator. And I don't know if this helps to visualize this a little bit better. But there's my tangent line. There's my delta x. Now, this is the curve. This green one is the curve. There's y. This is dy. And I'm going to bring this one up here. And that is the actual change. I can try and draw on here. I don't know if that's going to work. But that's delta y. And this is dy. Won't save it. dy is the change on the tangent line. For you to see it, whoops. For you to see it, I had to move this. Now it's going to all go away. I had to bring this down here. Okay, so this blue segment is dy, not delta y. This red segment is delta y. Delta x and dx are the same. That's this segment. That's delta x. This is delta y. Except they slid it again. Oh, wait, I didn't slide that one. I slid the blue one. Kind of cool, isn't it? I can do that. Yeah, that's just a little bit. I mean, that was just quick. That was all it was. So here is this segment. I got to figure out another way to do it. I'd like to be dragging it. I know how to do it. Just take me a little bit. That's something I could do quickly. Okay, yeah. This red one is the change in y, and the blue one is the change is dy. Come on. There's dx. That's the red one there right now. No, this is the change in the x. I have to do this because I didn't build this the way I should have, or yeah, it would take me longer. And then this is, let's see, will this let me go? Oh, nope, it won't let me do it. It's stuck on that line. I don't want it stuck on that line. That's the deal. So I would have to construct vertical lines here and put it on the vertical line and then hide the vertical lines. That just takes a little time, and I didn't have the time. So this is the dy, this is dx, delta x, and if I bring this point up here, that's the actual change in y. That's pretty cool. Okay, let's do a problem. Let's do this one. Y equals the square root of x. We're doing great. Notice that when I do part D here, I can use that on problems 11 through 14 tomorrow if I don't want to use the new thing. So, what we're going to get into tomorrow. But that's up to you. I just made a little notice there. Well, you know, C says sketch the diagram. I like to do the diagram first because I want to know what in the world I'm doing. Okay, girls, put your phone away, please. So, what does the square root of x look like? Okay, there are certain functions you have to know. This is one of them. It is a parabola. It's actually the inverse of the y equals x squared. Yep, it's the half. Okay. So I want to find the differential dy. I'm going to find dy and delta y if x is equal to 1. So let's draw that. It's not going to be drawn to scale. Then it's delta x is equal to 1. We're going to need our calculators. So delta x, which is dx, is equals 1. Where am I at down here now? 2. And I want to find delta y. Well, what's delta y? Let's break. Yeah, the change in y, which is equal to f of 2 minus f of 1. So this is 1, comma, the square root of 1. And this is 2, comma, square root of 2. So what's delta y equal to? There's no calculus here. Square root of 2 minus the square root of 1. You guys know how big square root of 2 is?
1.4.
404. Was it 4? Was it 414? What is it? 14? Yeah, it was, all of a sudden I just thought about that. Yeah, it's pretty close. If you're a carpenter, you know that number very well. And what's the square root of 1? Because I build lots of things using the square root of 2. Okay. So this is approximately, but pretty close to 0.414. Now that's the actual change in the y value. I knew the square root of 2, but if it was the square root of 3 or square root of 7, I'd use my calculator. I could estimate it. And then we're going to put a tangent line in here. So now let's see, I've done delta y, I've done that, and I want to find dy. So here's my tangent line. This length right there is dy. Is that bigger than delta y or smaller? It's bigger. So this will be an overestimate. My answer will be too big. Yes? Mm-hmm. That's right. Okay. Let's find dy. So if y equals x to the 1/2, what's dy? Oh, let's find dy dx. Let's do it that way. What's the derivative of that? Because that way you'll move over to the other way. 1/2 x to the negative 1/2. And I don't know about you, but I don't like x to the negative 1/2. So I'm going to change that. What is that equal to? Not x squared. Square root of x. Okay, now for the hard part. Let's find dy. This is algebra. It's 1 over 2 square root of x times dx. Yeah, either way, however you want to look at it. I found delta y. This is delta y. I want to find dy now. And I have everything, well, I don't have everything marked. This is delta y, isn't it? Yeah. So let's find dy. What's x equal to? That is the vertical change, because remember, m of my tangent line is dy over dx. Think of that as two separate numbers. Its slope is 3 to 1, or whatever it is. It's just a number. Okay, so when I did my tangent line, what's my x value? 1. So this is equal to, you'll be surprised at how accurate, well, this one's not very accurate, but this one's okay. And what's dx? That's the delta x. That's also 1. Because I don't need a calculator, do I? So what's dy equal to? 1/2 or 0.5. How does that compare to this? Slightly bigger. Dy dx is equal to 1 over 2 square root of x. Correct. 1. Dx is the length between here and here, which is 1. So I'm just doing the slope of this line, right? So this, if this is 1, then this height here is 0.5. The actual height is 0.414. Not bad, because delta x isn't very small. It's a pretty good estimate. It's just an estimate. They're going to ask you to estimate. It gives you 1/2. Yep. And that's just the arithmetic. The only calculus is taking the derivative.
But when you trace your fingers right by it, why'd you plug it 1 again?
Because this is the slope of the tangent line, and we drew it at x equals 1. So so what is the square root of 2 approximately equal to? The square root of 2 is this entire length, right? That's that entire length. That's the square root of 2. Using a little geometry, how big is this length? That's 1. Well, that's just 1. This is the square root of 1, right? Plus, and then you're going to add in this segment of the tangent line, which is 0.5. That's the approximate one. I need to bring this down. 1.5. Well, square root of 2 is approximately, we said it was 1.414. I need a calculator for that. If I don't have a calculator, I know it's 1.5. So what if I do the actual value of the square root of 2? This is the approximate. This is exact. Well, more or less. It's this height, 1, plus this delta y, which we said was 0.414. We used a calculator to do delta y, yeah. To do delta y, not dy. That's pretty close, isn't it? 1.414. Well, let's do the square root of 1.1. I'm going to get a new page, though. Yeah. You're using dy to do the approximation. So let's do a problem. Let's do 1.1. Yeah, we're going to do 1. Now, delta x isn't very small here, so I'm off. What about 1.1? How good can I get there? Whoops. I want to add a page. So y equals the square root of x, and I want to find the square root of 1.1. So I'm going to graph my function again. And I'm definitely not going to be to scale. I want to find the square root of 1.1. It's my goal. I don't have a calculator. Oh, well, who has a calculator? What is the square root of 1.1? Okay, that's an approximate answer to 1.1. You got to give me 3 places at least. Okay? I'm going to use calculus and find it another way. So, where would I like to draw my tangent line? What can I square root without any problem? 1. So I'm going to, here's 1, and I'm going to draw my tangent line there.
4.
Now, what's delta x? So x equals 1. What's delta x if I want to get to the square root of 1.1? Good. So I'm going to go over 0.1, and I'll be honest, I'm not going to be at all accurate on how this looks. That's 0.1. So this is 1.1. So this is the actual value right here. I don't want that. I'm going to use my tangent line because that's how your calculator works. The calculator does that for e to the x, does it for sine and cosine. It does all these little tiny tangent lines because that's easy. That's just number crunching. There is no table built into your calculator that says e squared is whatever it is. I have no idea what it is. Well, I do too. It's somewhere 2.7 squared. But they use the tangent lines because it's just adding, subtracting numbers. That's all. Okay. So this is dx, right? This is, distance here is what? That's dy. And dy, as long as dx is pretty small, it's pretty close to delta y. Let's see how close it is. Now, from the previous problem, because it's the same one, I don't want to redo this.
First, so if there's dy on the graph, what's delta y on the graph?
What's
dy is
the height of the tangent line? Delta y is the actual change. I don't know what that is. Not without a calculator. Some of you can work ahead, yeah? In this particular case, depends on the function as to whether it's bigger or smaller. Delta y is the actual change on the function. dy is the actual change on the tangent line. It's not that complicated. What's hard is thinking of a dy and dx separate as opposed to a derivative. Okay, so where did I draw my tangent line? I drew it at x equals 1. So dy equals 2 square root of 1. What's dx now? Not 1. 0.1. dx is this distance right here. Okay, can we do the math, the arithmetic? dy is equal to 0.1 divided by 2. That's what?
What?
Because it's 1.1. That's correct. Okay, what's 2 into 0.1? No. 2 into 10 is 5. I want to do it as a decimal because we know this, right? Okay, so what is this value right here? What is the square root of 1.1? Pretty close to. Well, I know this height. What's this height? 1. So the square root of 1.1 is approximately equal to the square root of 1, which is 1, plus dy. It's exactly equal to delta y. So that's approximately equal to 1.050. We took our calculator. No, dy is not. My approximation, this height here, is bigger than the real one. Here's the real one, and it's an overestimate. But you know what? Delta x is pretty small. That's pretty good. That's how your calculator works. Makes delta x is really small. It does number crunching. That's all it does. It's 1. Because I want the square root of 1.1. Look at this geometrically. This is 1 comma 1. This is 1 comma the square root of 1.1. Whoops, I need to fix this. I want this value right there. It's this length, it's all geometry, plus this height. Well, I'll show you another way tomorrow. Now, another application. So you got problems that look like this, but another application is this one. Oh, that must be 41 through 43. So the first ones have to do with these. So check your assignment sheet, but this has to do with what I just did with the differentials. And then this has to do with this application. If you're a machinist and you're building something and you have to make these little discs, you're not, you know from science class, you can't possibly come up with a radius of 24 every time. You're going to be off. 24.1, a little bit less than that. And so what we'll do is have a tolerance of 0.2 centimeters. Now, you guys, this is an 8th grade Algebra 1 standard. I'm not saying I agree that it should be there, but it is there. So I'm going to draw my disc. We will need a calculator to do this the way you want to do it. The radius is 24. And the error in the radius, that's the change in r. So when I'm building this disc, I can be off. I'm okay if I'm off by 0.2 centimeters. And actually, they're much closer than that. Machinists are not that far off. They can't be. Because if it's a little bit too big, it's not going to fit in whatever part I want to put it in. Yeah. But just to keep our numbers somewhat simple, we'll do this. Now, it says use differentials to estimate the error in the area. How do you find the error in the area? See, guys? It would be the area at, if you made the mistake of going too big or too small, minus the actual area that you want, the perfect one. Well, what's the area of a disk? They do expect you to know this. Pi r squared. Nope, no holes in it, just a disk. Like a penny. A quarter. Okay, well, I know what 24 squared is. You guys know what that one is? 576 pi. Okay, for this one I have to do 24.2 squared. Now this, by the way, is the actual error. This is the real error in the area. Try to say that fast. What's 24.2 squared?
576 plus squared.
No, it isn't. I wish. This is the actual error in the area. If you make a disk with 24.2, you're a little bit off. That's the maximum area you can have and have this part work. This is the actual one. This isn't a perfect world, but we never measure it perfectly. That's what I really want. Sometimes we will measure it perfectly, but as a general rule, there's going to be an error there. No, the area at 24. Function notation. Okay, what's 24? Who's got a calculator? 585 point what? 61? Oh, 4. Minus 576 pi. If you subtract that, that's 9.645. Okay. That's actually calculating the area when you make the worst mistake you can make relative to the actual one you want to have. I can use differentials, which is a lot easier. I don't need a calculator, surprisingly enough, to do this. And so this is the change in the area, delta A. I'm going to use differentials. I want dA. What's the derivative of the area, and what are we taking it with respect to? That's right. The change in the radius as the area changes. What's that equal to? Yeah. What's the derivative of that? Does anybody recognize that formula? That's the circumference, and I've seen problems on the exam where they expect you to recognize that formula. Okay, solving for dA, what's dA equal to? It's equal to 2 pi times the radius times dr. This is kind of in the way, but we'll work around it. Okay, now remember, dA and delta A are not the same, but they're pretty close as long as dr is small. So let's try this. It's 2 pi. What's my radius where I drew my tangent line? 24. And what's my dr? It was 0.2, right? Yep. And we multiply that out. You're saying, I can't do that without a calculator. Yes, you can. What's 2 times 24? That's 48 pi times 0.2. And what's 2 times 48? 96, count back 1. 9.6 pi, 9.64 pi. Wow. You did that without a calculator. You're in the shop and you got to figure out how far you're going to be off. You might have to actually work on a math problem. It's a lot easier to do with the calculus. That's the approximate error in the area. There's the real one. This is exact. This is delta A. This is dA. Remember, that's a change on the tangent line, not on the function. This is approximate. Okay, then it asks for what is the relative error. Hey, guys, how do you find the relative error? You remember from science? Take 9.6 pi divided by the actual area, which is 576 pi. And that works out to be 0.16 repeating. How do I write that as a percent? Ricardo, how do I write that as a percent? Multiply by 100% and I'll get, oh, it's 0.16. Sorry. No, it's my fault. That's pretty small error. But, so you end up getting 1.6 repeating percent. Now think about it. You are manufacturing iPads. That means out of approximately 100 iPads, approximately 2 are going to be defective. Is that good business? No. I don't think I want to buy an iPad if 2 out of 100, 1 out of 50 are going to be bad. So they have to have this error way smaller than that. But you will run into it. My exchange daughter last year got a Kindle, and she happened to get a defective one. So we sent it back and got a new one. Yeah. Oh, they'll do that. But it worked for about a week, and then all of a sudden it stopped working. And actually, and Mrs. Hersman has one of the CAF CX calculators, and hers worked for about a day and stopped working, and we had to send it back, and she has a new one now. Yes, they do have defective machines out there. You just hope you're not the 1 in a million or whatever it is. Okay. We still have some time to do some problems out of 4-4. So give it a try on this assignment. You must use differentials. You are not allowed to use, if you want to do the exact on your own, fine. But that will not get you points. Okay. Do we need to do problem 6? 6 is on the answer sheet on Mrs. Hersman's copy. That's at least what I found out there. If you're on Blackboard, it might be my answer sheet, so I don't know. I think 6 is there. We can do number 3. 6 is on the other recording. What is the smallest perimeter possible for a rectangle whose area is 16 inches?
Which one are you working on?
This is 3.
This is number 3, yeah. I can do this.
No, he said 3 is the only one he can do.
I know, but somebody else had a question up.
Can you like hit us up over like
We'll get 3 of them done if we get working here. Okay, shh. I want the smallest perimeter.
Where's my sheet?
Okay. And it says the area equals 16. Okay, guys? I think it's in the setup. I'm not sure where the problem is. But, what do you want to label the sides as? X and Y? Okay. What's the perimeter equal to? 2x. Okay. And it says the area is 16. So the area is equal to, okay, I want the smallest perimeter. This is the one we're going to minimize. I have to get rid of x or y. Which one do you want to get rid of? Okay, that's fine. So y equals 16 divided by x. So let's substitute it in here. And this one's, so it's 32 over x, correct? Now, can I close the interval? You guys? What has to be true about x? Look at your formula. It has to be greater than 0. And in fact, it could be infinitely large. Well, it doesn't matter. All I worry about is the variable that's left here is x. And it's an open interval. So guess what? Max-min existence theorem does not apply. So we're going to find the derivative. So this is, because you can have an infinitely long rectangle, the height will be infinitely short. Pretty pathetic rectangle, but yeah. There's no limit to it. And even the fact, even if
that area has to be 16, so
I can think of a very tiny number and multiply by another number and get me 16. Or I can take a very large number and multiply by a very tiny number and get 16. It's open. 15.99999999999. Yes, you can go off to infinity with it. Okay. So this is plus 32x to the negative 1. Even the fact that it's not closed on one side is enough to throw out the max-min existence theorem. I'm not happy, but I can argue this. What's p prime? Did you guys try this? Now, before I do that even, I want to rewrite this. I don't like that. Okay, well, I have a singular point at x equals 0, but you know what? X equals 0 is not in the domain. You can't add anything, Grant. You have to set it equal to 0. So 0 equals 2 minus 32 over x squared. So 2 equals 32 over x squared. And then I'm going to do what? Cross.
Multiply.
So 2x squared equals 32, so x squared equals 16. And this is a rectangle. X would be positive or negative 4, but it can't be negative 4 because that would be a negative length. Don't forget the negatives, because if it's not a rectangle, if I change this to say, girls, if I change this to say the product of two numbers is 16, now we can have negatives. It's a rectangle. That's why we had to not use 0. Can't use negatives. So we're going to, yes. Yes. Nope, you have to show the process. Because it might not have been at 4. It might have been at 4.1.
What 4.1 if you guessed it checked?
You would not find it. It might have been a pi. You would not find it. So you have to do the process. Remember on the exam, you must convince the reader you know the calculus. Okay? Okay, guys? There's p prime. I have to do a derivative test because I don't know if it's the maximum. But it was a maximum or minimum. I don't know if it's a minimum. But I'm going to tell you that they're not going to trick you. This is always going to give you, if it says smallest, it's smallest. Then I could fudge the sign chart if I want, but we're going to do it. Okay, so 4, if I take 1, if I put 1 in here, this is 0. Is that positive or negative? It's negative. And this side, if I put in 100, it's positive. That tells me, because the derivative is negative, the function's decreasing, and it's nice and smooth, and then it's increasing. So there is a minimum. Are there any other candidates where this could turn around and do something like that? Just 0. 0's not in the domain. There's no other candidates. So my function will look like this, and because it looks like this, it's an absolute minimum. It never turns around again. There are no more candidates. So sometimes you have to do a first derivative test. Because look at our original function. I can't have 0 in here. What's p of 0? Undefined. Can't do it. Now, if it had been open, I would have had to evaluate that, but that would probably be a maximum. Okay. Do we need to do 6?
Yes.
Let's look at 6. 6, we're going to need a graph. We can do this. And it's y equals 12 minus x squared. And I want to find, I don't know, I've forgotten already. It says a rectangle has a base on the x-axis. Its 2 upper vertices are on this parabola. Well, can you draw the parabola, Cole? When x is 0, what's y?
12.
12. Is this an even or odd function? Even, and it opens down. So it looks like this. Not great, but it's okay. I'm going to put my rectangle in here. And it's not really clear how it's centered, but it is centered that way. And I want the biggest area. Well, this distance, why don't we call this x? Because now it relates to the coordinate of the graph. Hey, girls? That's x. Well, then what's this distance? X. What's true about x? Is it negative? No, it's always going to be greater than or equal to 0. What's this distance? Y. Okay? And I'm going to go back and read the question because I forgot it already. I want the rectangle with the largest area. So area, how do you find area of a rectangle?
X.
Length times width. In this case, what's the length? Y times 2x. I need to eliminate x or y. Well, I can. It's easy. Because you know what? I know what y is. What's y? 12 minus x squared. They told me that. It lies on this curve. That's the y value, 12 minus x squared. So I'm going to put that right in here. Oops, for y. Okay, so the area is equal to 2x times 12 minus x squared. Oops. And I have part of my interval. I have x starting at 0. What's also going to be true? What's the smallest y can be? Because x was measured from here to here. If I measure it from over here to over here, I'm in trouble. Now I can't use this y because it's not part of the coordinates for that graph. So what's true about y? It's greater than or equal to 0. So 12 minus x squared is greater than or equal to 0. I want to close it. Mathematically, you're right. Geometrically, I don't want to close, but mathematically I do. And look at this. If this is the rectangle centered here, see, x is getting closer and closer to 0 there, isn't it? But what about over here? What's the y getting closer and closer to? 0. I'll show you that one now. So I have to solve this. So 12 is bigger than x squared. I don't like my x squared over there, so I'm going to move it. So x squared is smaller than 12. And then how do you solve that? You square root it. When I square root it, I get the absolute value of x is equal to the square root of 12. So x is equal to the square root of 12, girls, or the negative square root of 12. Can't be negative because x represented a positive number. Okay, so there we go. There's our interval. It starts at 0 and it goes to the square root of 12. It's the y-intercept. I'm sorry, it's the x-intercept. So all I have to do now is find my derivative. And is that a continuous function? It's not a closed interval? It's nice. It's so much easier. Square root of 12. So this is 24x minus 2x cubed. Take the derivative. It's 24 minus 6x squared. And then what are we going to do with that? Set it equal to 0. Now, can you guess and check on this? Sure. So I'm going to add 6x squared to both sides. Because they're not interested in the algebra. They're interested in the process. Now, what's x going to give me? Two values, but x has to be positive, so x is going to equal what? 2. Be careful, because if it wasn't a geometry problem, x could have maybe been negative. And now I'm just going to make my little graph here. It's right here. And I'll move this down here. And here I have x, and I have my area and my endpoints, which were at 0. Whoops. I always do that. Square root of 12. Those are the endpoints. And then I have this 2. And we have the max min existence there. It's actually clear to the reader you're going to do that. Okay, what if x is 0? What's the area?
0.
Yeah. What if x is the square root of 12? What's the area? It's 0. Put square root of 12 in there, right here, and square it. 12 minus 12 is 0. So these are 0. They didn't ask for the area. They asked for the dimensions. Obviously, this is the min, and because the max min existence theorem guarantees a max, this is the max. You're going to have to say that in some sort of words. Otherwise, you'll have to evaluate it. But we want the dimensions. So they're asking for what's the length here. What's the length? Length equals 2x. So how big is that? 4. And then the width is equal to y. And what's the y value? It's 12 minus 2 squared, or 4. So the width is 12 minus 4 is 8. So the dimensions are 4 by 8. What's the area? 32. Wouldn't hurt to find that, but because once I do that, I can do this. That's 32. There, now I've got absolute proof. Is that okay? You need to try these on your own. Now, I know we're going to get stuck on this if I don't do this a little bit. Now, Mrs. Hersman and I did this problem in 2 different ways. Let me draw it. That'll help. Okay, Adam? This is up online. But we're going to put a cylinder, a right circular cylinder, which looks like this. And we want to find the maximum volume. Okay, you do not have to know this formula. They will give it to you. But the volume is the area of the base times how tall it is. Call that h. And the area of the base is pi r squared. Guys, I want to get this done. Okay? That's what I want to maximize. I don't want so many variables, Cole. I don't want r and h. So what I'm going to do is put this into a sphere. Oh, not a very good sphere. And we want to get rid of some variables. And we can. It'll only take a second. This is the radius of the sphere. I can draw it anywhere I want, but that's convenient. That's 10. This is the radius of my cylinder, and this is the height of half of it. Of the sphere is 10. The radius of the cylinder, I don't know. The height of the cylinder. What is the height of the cylinder, though? No, it's 2h. Because I didn't want to make this h and have to use h over 2, because I didn't want to do fractions, personally. So I'm going to put that right in here. It's pi r squared. Capital H is 2h. And now it's a much easier problem. Oh, not quite yet. 2 pi r squared times h. Here's the problem. I don't want 2 letters there. I want only 1. Look here at the picture. What's the relationship between r, h, and 10? R squared plus h squared, Ryan, equals 10 squared. Do you want to solve for h and have a square root in here and put that in here, which is what Mrs. Herman did? Or would you rather solve for r squared and just put r squared in there? You got to get rid of r squared or h. Take your pick. But it seems that's harder. You can do it that way. Because this is a lot easier to put that in for r squared. Sorry. Pythagorean theorem. And this is all online and in color, plus it's in the video. So I'm a little bit more done in the other class. Think of restricting the domain. It can be done. Okay, don't forget to do your homework.